My name's Andy. I work for Schlumberger Wireline based in Luanda, Angola, and I'm presenting on behalf of Andrea Hughes today, who wasn't able to join us. Andrea is the engineering team lead for BP in Angola. I was her counterpart within Schlumberger for the campaign. So I was there for the design, execution, and the follow-up of this intervention campaign. It was a 9-well campaign that we did for BP in Angola. We did it from an intervention vessel. They were all subsea wells and anywhere from 1,000 to 2,000 meters of water. So it was actually a first riserless intervention that we've done that anybody's done in Angola. So we did it aboard the Muck installer vessel. Oceaneering provided all of the subsea lubricator grease injection system. And we actually had great success on the campaign. So what I'm going to go through today is one of the wells specifically, and just look at some of the challenges that we had with that well, how we overcame this. There was a lot of advanced planning, which is actually what got us through not just this well, but a lot of contingency planning for the entire campaign. So I'll go straight into this well. Some of the interface testing we did. I mentioned the contingency planning, which was extremely important, as it is in most cases. But when you're performing an intervention from a vessel as opposed to a platform, it's even more critical. Then we'll take you through the execution, and if you've got any questions, we can go through those as well. So this is the well that we intervened in. This is one of the 9 wells that we intervened in. So this well was initially designed to produce around 9,000 barrels of oil per day. Prior to the campaign starting, the production was only about 5,000 barrels per day. After looking through the job files of the history of the well, it was realized that there's a high likelihood that the FIV that was installed in the well had actually not opened completely. So the skin of the well had a value of 40, which is extremely high. If you had a barefoot completion, your skin should be 0. This was a gravel pack completion, so we would have expected skin values much, much lower, close to 0. So, and this well was different from the rest of the wells in the field. It didn't make any sense as to why this specific well was suffering from such a high skin value. So the objective of the intervention in this well was to reduce that skin and increase the oil production. So there was a couple of ways that we can do that. Like I said, it was the FIV that was suspected to not be fully open. It's got a shifting tool, dummy shifting tool that you use to shift the valve open during normal drilling operations. So we could have used that, but as a built-in contingency, we had a milling tool with us, so that if for some reason we weren't able to shift it open, we could go and mill the valve open. A couple of challenges in the well. There was a restriction in the well above us that was less than the shifting profile that we needed to access. So there was a possibility that with the normal shifting tool, we wouldn't even be able to access the shifting profile. We'd planned 13 days for this intervention, and I'll show you at the end how we actually did. So because of the complexity of the well, we started out by doing some testing. So there were 3 different things that we wanted to test. First, we wanted to see if we could shift open this FIV with a standard shifting tool. So BP actually had an FIV that we got from our completions guys. We rigged it up horizontally in the yard with 2 joints of tubing, the same size tubing and sort of the same configuration that it was in the wellbore. So there was a pup joint directly above the FIV and then full joints above that. So we did the space out exactly what it was in the well so that we could work on our space out and make sure we knew exactly where everything was going to land off. The second part of the SIT was an LIB the initial idea was to use that to confirm if the FIV was open or closed. Because again, at this point, it was still suspected that the FIV was partially closed, and there hadn't been any interventions, so there was no way to confirm if that was the actual issue. And then the last part of the SIT that we did was to mill through the FIV to see if it could. We hadn't milled through a partially closed FIV previously. So on the bottom there you see the FIV with the joint of tubings configured as they were in the wellbore. We rigged up the Resolve tool string, which is what Schlumberger call it's our family of tools for powered intervention. So in that, because this was a deviated well, the FIV is at about 80 degrees deviation. So we had to have tractors rigged up behind it, and obviously in the yard we're at 90 degrees. So we use the tractors to convey the dummy shifting tool through the tubing, down to the shifting profile. And this whole time we're monitoring inside the logging unit what our forces are, what's your tractoring speed, what's your tractoring force, what's your shifting forces, so that once we get to the job, we have baseline parameters to compare to. So we confirmed that we can easily shift the FIV open. Actually, even without the tractor, when you're in the yard just by hand, you can shift the FIV open and close quite easily. So that's why after doing that part of the SIT, we figured, yeah, this is really probably something to do with the FIV. It's jammed for some reason. The next part of the SIT was we'd planned initially to use a lead impression block to confirm if the valve was open or closed, or sort of what the degree of angle would be. Now, for any of you who've used LIBs before, they're also nicknamed lead guessing blocks. Sometimes what you get is very inconclusive. And that's what we had here. If you look at the picture on the lower right, this is the impression that we got after running in hole, or after doing the SIT. So this was a tool string that we used here. We put that, again, deviated well, so you don't have slick line, you're not jarring down on it. You're tractoring into the well. You've got this lead impression block on the bottom of what we call linear actuator or stroker tool. So we run in the well, we have some anchors that open up, and they land in that tubing. Once those are anchored off, the linear actuator strokes out and applies a force onto the FIV. So we spaced out so that the lead impression block is only a few inches above this ball valve. And then once we're anchored, we apply a downward force so that we can create an impression on this block. Now, this is the impression we created. And as you can see, typical for an LIB, it's inconclusive, right? There's a little bit of an impression here on this corner. The other sides of the LIB are much more square. But because this ball valve is partially closed, what you're really just getting an impression of is sort of the LIBs running kind of into the wall, into this concave shape of this valve. So had you gone into the well and done that, you would have come back and not really known, am I really landing off on the FIV? Is that just wear from the side of the tubing? Is there something else going on? So we actually decided to not run the FIV, or sorry, to not run the LIB on the basis that that's an expensive trip in the hole if it comes back and looks like this and we can't tell anything. So we actually ended up using another logging tool with a smaller OD, which once we did the operation, confirmed for us that the FIV was partially closed because we could see the tool go in and then drag a little bit on the way out. So we did a drift run with a multi-finger caliper, and a bullnose on the bottom, and that was able to confirm for us that the FIV was partially closed. The next part of the SIT that we did was to actually mill out the FIV. Now, the FIV that we had was in perfect condition, so we actually had to open up the engineering drawings, drill some screws circumferentially around the FIV, and lock it into place so that we could perform our milling trial. And it worked perfectly. So in the top left, you see this is your ball valve on the left-hand side, and you can see your mill bit kind of there in the top right corner. And in that center picture, you see the portion of the ball valve that we milled out. And then a through-bore axis on the lower right-hand side. So again, we set this up in the yard, the tools, the equipment, the personnel that carried out the operation were the same guys that went offshore and did the operation. So we had the baseline logs, we knew what it was supposed to look like. In fact, you can see it here during the SIT. You get a baseline on the left-hand side there for what your torque is supposed to be. And then you obviously see your torque increase on the center graph during the operations. And on the right-hand side, you see that torque drop off after you've broken through. Now, the whole operation took 40 minutes. Your mill bit is actually only traveling a few inches, so it's actually difficult to see, and you can't tell. I mean, obviously, when you're doing this in the well, you've got about 3,000 meters of 4,000 meters of cable in the well, so you're not going to see a couple inches of movement. So it was important that you monitor all that with the tractor. So the tractor has an auto mill function which is set. So you're setting your weight on bit the same way a driller would if it was drilling a rig, or drilling a well. So you set that weight on bit, you control your torque so you don't lock up. During the execution, you see a very similar signature, a baseline torque value that matched milling torque values that matched those similar to what we had during the SIT. And then we milled through it in 38 minutes when we were offshore. And now because it was only partially open, the piece of ball valve that was left, that was remaining, we weren't able to recover, but we knew that going into it. Based on our assumptions and based on the trials from the FIV or from the SIT. So all in all, the intervention for this well and the campaign as a whole was a huge success. So you see there, the mechanical skin was reduced from 40 to 0, which is perfect, exactly what we wanted. And then we increased the production of the well by 3,500 barrels of oil per day, which we were all extremely excited about, BP especially. And we did it with very little NPT. We beat the planned times, came under the NPT for the well. So it was a brilliant success. For us, for Oceaneering, for BP, the well and the campaign went really, really well. So on this campaign, there's several other wells that have similar success stories.